Hello, my name is Scott Sheeter. I'm a principal engineer at Slipstream. Welcome to the Cree SmartCast lighting demonstration video. In this video, we'll provide an overview of a demonstration of an advanced lighting control system at 3 Department of Defense facilities. This presentation is an overview of a field demonstration of the Cree SmartCast system at 3 Department of Defense facilities. The project was funded by the Department of Defense's ESTCP program. Within this presentation, I'll provide an overview of the project, provide more detail on the Cree SmartCast system and the retrofit sites themselves. Then I will outline the project's results as well as key takeaways and lessons learned. This project was completed in 2020. It was a demonstration of the Cree SmartCast system at 3 facilities across 2 Air National Guard bases in Wisconsin and Michigan. The main objective of the project was to evaluate lighting control retrofits at these sites in terms of ease of installation and commissioning, measured energy savings, lighting quality, installed cost and economics, and occupant satisfaction. We also set out to accelerate the deployment of advanced lighting controls, which is partially why we're here today. Here's a brief overview of the lighting system. It included luminaires with an efficacy of 130 lumens per watt, equating to fixture powers between 25 and 30 watts. We utilized the 4000 Kelvin and 90 CRI fixtures to align with Department of Defense requirements. Like all luminaire level lighting control fixtures, these fixtures had integrated occupancy and daylighting sensors, allowing the lights to be turned off during periods of no occupancy and dimmed during periods of sufficient daylight. The fixtures communicated wirelessly with each other and dimmers. The Wisconsin site was a 1,600 square foot office building. The spaces retrofit were an open office and 2 private offices. The existing lighting system was fluorescent fixtures with no automated controls. There was significant daylight present in all spaces. The Michigan base had 5,500 square feet in total across 2 office buildings. These spaces included open offices, 10 private offices, 2 conference rooms, and associated circulation spaces. The existing lighting system was similarly fluorescent fixtures with no automated control. The daylight availability varied from significant in many private offices to minimal in core areas. To illustrate the energy savings components, here is an idealized day of lighting power. The existing lighting system in blue comes on to full power when the first occupant arrives in the morning. It stays on at this full power until the last occupant leaves in the evening. The retrofit system similarly comes on to full power in the morning. However, its full power is significantly less than the existing fluorescent system due to the higher efficacy of LEDs. Task tuning further reduces this power, reducing overlighting in the space. Lighting power is then reduced throughout the day during periods of no occupancy and significant daylight. From this idealized example, we transition to actual monitored data. Here we see the lighting power of an entire lighting circuit, both before and after the retrofit, on a typical weekday. Before the retrofit, the lighting turns on and is pretty constant. You can see a short period at the beginning of the day where only one of the multiple spaces is on, but for much of the day, all the spaces are on to their full power. After the retrofit, you can see multiple spaces turning on separately, which could be either from manual operation or via the occupant sensors. You can also see the dimming due to the daylight sensors. The net effect is a considerable reduction in electric power. This table outlines the calculated savings across multiple performance metrics. As you can see, the electric energy savings was significant. It averaged 2.5 kilowatt hours per square foot, or 69% lighting energy savings. This equated to roughly proportional savings across peak demand, greenhouse gas emissions, and utility costs. The utility cost savings averaged 42 cents per square foot across all spaces. We wanted to understand the proportional savings of each energy savings component. Through analyzing the daily profiles across each space, we calculated that 48% of the energy savings was attributable to the switch to LEDs. The remaining 21% was from the controls. Note that these proportions would be different in spaces with more variable occupancy or different daylight availability. One of our performance metrics was to bring the light levels in each space into better agreement with the Unified Facility Code recommendations. Note that the UFC recommendations are roughly equivalent to the Illuminating Engineering Society's handbook recommendations, with area-weighted averages of between 24 and 30-foot candles across the office, conference room, and corridor spaces. Prior to the retrofit, the spaces were generally overlit, being 29% higher than the UFC recommendations. The notable exception was at Truax in Wisconsin, which had illuminances in very good agreement with the UFCs. During the project's design, we developed photometric models of each space and used these model predictions to calculate the amount each lighting zone should be task-tuned in order to best bring them in line with the UFCs. During the retrofit's commissioning, we then applied these task-tuning set points to the lighting system. This process resulted in an improvement to within 14% of the UFC recommendations. However, we noted that Truax in particular was well below 30-foot candle targets. This was corroborated with occupant feedback of too low light levels. We received similar feedback from some of the private offices at Selfridge. We therefore revisited each site and retuned the light levels. The adjusted column shows how we were able to increase the light levels to within 6% of the UFC recommendations and also improve occupant satisfaction accordingly. Besides taking occupant feedback during and shortly after the commissioning process, we also implemented an occupant survey both before and after the retrofit. The results of our occupant satisfaction survey have been overwhelmingly positive, even with the overall light levels generally being reduced. Here are the pre- and post-retrofit results when we asked how satisfied occupants were with their light levels. Before the retrofit, there was a wide range of satisfaction with their lighting system. In general, the open office occupants had a wide range of satisfaction, as can be expected, since individual preferences vary and the lighting provided was uniform. In the private offices, the feedback was more positive, but a couple of occupants were very dissatisfied with their lighting, likely due to their having very high light levels with little controllability. After the retrofit, you can see the high amount of extremely or somewhat satisfied respondents as compared to post-retrofit, or before the retrofit. The overall score improved from 2.5 to 1.6. Remember that 1 was extremely satisfied and 5 was extremely dissatisfied. The two remaining dissatisfied occupants were in private offices. After this survey, we circled back to improve their light levels. We unfortunately didn't re-administer the survey, so we're not sure how this improved over our overall score. But it's possible that we won't be able to please everyone, which shouldn't come as a surprise. We found similar results when we asked how the occupants were satisfied with their ability to control their lights. Our project capital costs were higher than expected at over $8 per square foot. Factored in a utility program rebate and our project's utility bill savings resulted in a simple payback of 20 years. Digging into why our project costs were so high, we found 3 contributing factors. The expected installation time per fixture was 0.4 hours, as estimated by an electrical contractor during the proposal stage of our project. The actual installation times per fixture ranged from 0.6 to 1.2 hours, which translated to much higher labor costs. The higher actual labor hours may be due to the small areas associated with our sites. For each site, there's a fixed amount of time associated with traveling to the site, unloading fixtures and getting set up, and then understanding the installation process. Once this is complete, the installation of a given fixture goes relatively fast. However, since our sites were small, the fixed time became a larger component of the overall labor cost. We originally estimated a fixture density of 80 square feet per fixture by assuming a fixture space of 8 by 10 feet on center. The actual fixture density was much lower, between 35 and 52 square feet per fixture. This translated to more fixtures and a higher materials cost per site. This higher fixture count per site was in part due to the prevalence of private office and conference rooms, which tend to have higher fixture densities than open office. However, the selected site open offices also had lower fixture spacing and correspondingly high fixture counts than our original assumptions. During the proposal stage of this project, we originally assumed a market of 18% based on input from electrical contractor. This is significantly lower than the 34 to 77% markup from the demonstration sites. The reasoning behind the increased markup is unclear. However, one potential reason may be the research nature of this demonstration. Contractors and distributors may have increased their bids to offset their uncertainty in installing a new high-end system that they had no previous experience with. Other projects had lower costs, ranging from 3 to 5 feet per square foot. Assuming similar utility cost savings would give a simple payback range of between 7 and 12 years. Note that this is compared to an existing baseline. Project economics would likely improve if fixtures were end-of-life, shifting the baseline to LED and minimal controls as required by the UFCs. We learned a lot throughout the demonstration project. The first thing was to create a control matrix. This control matrix outlined our assumptions regarding how each space's lighting would be controlled. It included information about timeout periods, task tuning set points, and other control settings. The facility staff and office manager reviewed our assumptions and provided feedback based on their understanding of the space's needs. This feedback helped optimize the controls in each space and minimize subsequent occupant complaints. We further found that photometric models are useful in estimating the illuminance in the post-retrofit spaces. However, they're not always accurate. In retrospect, our photometric models could have been improved by more specifically representing interior furniture, particularly tall partitions and associated storage cabinets. Confirming light levels with spot measurements and informing light level set points with occupant feedback is highly recommended. Occupant satisfaction with our system was high, and so was the facility staff and installer satisfaction. They found the system easy to install, maintain, and adjust. The main challenge is the system's high cost, which makes economics challenging. However, the trend in decreasing costs is encouraging. The Northwest Energy Efficiency Alliance has published data to this end. Contractor education is important to help further reduce costs. As they become more comfortable with these systems, contractors are more likely to right-size their bids. Cybersecurity is increasingly important. This demonstration was of a standalone lighting system that didn't connect to any other systems, such as the building's network. I believe the other presenters will briefly address the increasing cybersecurity challenge when connecting lighting to other systems. Despite the challenges we saw on our project, advanced lighting controls remain a clear opportunity to capture significant energy savings on lighting retrofit projects. This technology promises to have improved cost effectiveness and usability in the future. For more information, the following Department of Defense website contains an overview of the project, a final report, and associated executive summary. This brings us to the end of this video. Thanks so much for watching.